Okay, it's recording.
So thanks so much again, Professor Mike Lanagan, for joining us today to give us a seminar for the PAC Fellowship. Just as an introduction, PAC Fellowship is a National Science Foundation funded program. It provides funding for US students to go to University of Kiel in Germany to conduct a short-time research. And thanks to University of Kiel and the mentors there, they have been very good hosts for our students, providing them training, both hands-on and educational information. And so it's a very good program from our point of view that it not only provides collaboration opportunities for students, but also faculty have been able to interact with each other and develop collaborations and partnerships through this program. And as a part of this program, we organize these PAC Fellowship seminars where we invite experts like yourself, Professor Mike Lanagan, to provide information on an emerging topic to our students and researchers. And hopefully this will excite them to pursue some of the things they learn in these seminars. Professor Mike Lanagan is well-known researcher in the areas of microwave dielectric materials, electronic materials, high energy dielectrics for pulse power application. And he has been at Penn State for a very, very long time, served in many different administrative capacities and also in research programs. I think before coming to Penn State, Professor Lanagan used to work at the National Lab, and so has experience about how things operate at much more national scale, and has been able to apply some of that information in creating programs and executing programs at Penn State at much larger scale. He's probably one of the most prominent person on the campus at Penn State when it comes to microwave measurements, and I think his expertise is leveraged by many companies and many universities all around the country. So I'm very glad that he was able to find time from his very busy schedule to come and talk to us about microwaves and this very fascinating topic of 5G. We all hear the word 5G, and I think today we'll be able to learn what this really means. So thank you so much, Professor Lanagan, for taking up the time.
Great. Yeah, thank you for that great introduction. Really looking forward to presenting and then hopefully creating some new ideas for collaboration. Let me share my screen. Let's see. Hopefully you can see it. Well, let's see.
Yeah,
you did see. Let's see. Share. All right. So hopefully you can see the screen, and let me bring up the presentation.
We can see it.
You can see it. All right. Fantastic. And all right. Well, yeah, as I said, it's a pleasure to present to Kiel University and the faculty and also the student fellows in terms of what I'm going to talk about today. Really focus on insulating materials. We call them dielectrics. So these are non-conducting materials, typically very wide bandgap materials that allow us to look at the electromagnetic wave propagation through them and use this electromagnetic wave performance to do certain things in certain applications in medicine and telecommunications. So you may wonder what the relationship is between the medicine and telecommunications that I mentioned in the title. I'm very focused on magnetic resonance imaging shown here, and also 5G. And if you look at the electromagnetic spectrum, here are the frequencies shown here, essentially looking at the low frequency. In this case, it would be on the order of a megahertz and higher. We can see that actually the MRI frequency in the 100 megahertz range and in the gigahertz range for 5G, they're actually, if you look at this scale anyway, they're not really that far apart. So a lot of the physics and the materials we think about are pretty much related between these two fields of magnetic resonance imaging and 5G. So that's sort of the common aspects. And of course, during the presentation, I'll show some things in terms of materials of how we think about this frequency region. I love MRI. It combines many things that I've been interested in over the last 3 decades of research. Superconductivity. There's a lot of interest in applying superconductors in many applications, but probably one of the first ones was magnetic resonance imaging, mainly because you needed a very strong magnetic field to align the proton spins, which brings us to quantum mechanics. My particular interest these days is in electromagnetics and material science and how they relate to increasing the performance of a magnetic resonance imaging system. And then, of course, neuroscience is a very, very big topic these days, and MRI is used quite a bit in neuroscience, and in particular, because we can look at functional MRI, which is really looking at the brain activity through an oxygen depletion signal in the brain, because you're basically using up the oxygen within certain regions as you think. Basically, they call it a bold signal, and we can then basically watch where people's neurons are excited when they have a certain stimulus. So basically, that's where the neuroscientists are getting involved with MRI. Basically, on the hardware side of magnetic resonance imaging, if you look here, again, this is a big superconducting coil cooled with liquid helium, probably also liquid nitrogen as a jacket around this. And this supplies very large magnetic fields, 1.5 to 7 Tesla. Generally, at least in the US, most of the MRI machines are 1.5 Tesla. And lately, though, a lot of research areas, research universities are really pushing towards 7 Tesla, mainly because the signal to noise ratio is increasing quite a bit as we push up in magnetic field. And then associated with this large DC static field generated by this coil, the superconducting coil, we also have this RF field, magnetic field, that's superimposed on that DC. And I won't get into the MRI physics too much, but basically you need both a DC magnetic field and an AC magnetic field to really see the response of the brain, or whatever anatomical thing you're looking at in terms of the signal. So we talked about the magnetic field, DC. The RF field corresponds to this. So basically at low field, we have something on the order of 60 megahertz. And as we push up in magnetic field up to 10 Tesla, for example, we're up to 500 to 600 megahertz. So the coil itself basically sends and receives RF signals in this frequency range. And of course, what's happening now is we need faster scan times. Anyone who's had an MRI realizes it's much slower than, say, a CT scan. Sometimes half hour, 45 minutes in this claustrophobic tube is an issue. So we're trying to really increase the signal and noise ratio, so then we can then decrease the time or have better resolution. So that's the goal of our research at Penn State, is to figure out ways to basically couple RF energy in and out of the brain a little bit more efficiently, so we can increase the signal and noise ratio. Just as an example, this is a small MRI unit that we have at Penn State. The bore size here is on the order of maybe about 20 centimeters, something like that. And so then what we can do there is do animal research. And what we've done is we replaced the coil with a ceramic resonator, and I'll get into why we do that in a little bit. But basically, this supplies the RF field I was talking about. And then what we can do is we can put our species, our samples into this hole here, and then that whole assembly can go into the MRI unit, and we get these really nice images of say, a zebrafish. We can see lots of the anatomical sort of features of that zebrafish, basically because we have a very large signal and noise ratio in this sort of scenario. And basically because of the electromagnetic wave coupling and very efficient coupling in and out of the sample. So let's dig a little bit deeper. What I'm really going to focus on is this RF coil, right? And coupling this energy in and out, making it more efficient, increasing the signal to noise ratio. And the main driver for that is something called functional MRI. And in this case, we can actually look at the brain activity with this blood oxygen level. It's called a bold signal. As the neurons fire in the brain, we see a reduction of the oxygen is being used up, and then actually the iron in the blood basically changes a valence state and then changes the susceptibility locally around that region. And so that's an indirect way of looking at brain activity. But the problem is you have to integrate a long time to get this sort of signal. And so to basically look at more of a real-time thinking pattern, we really need to get a higher signal to noise ratio, and we need better resolution, which also translates to a higher signal to noise ratio. So how do we do that, right? So how do we get more signal in to the brain? And one thing we need is also the signal coming out. And so what happens in an MRI unit, this is the quantum mechanics part, is where you send the signal in, you basically orient the spins of the protons, and then over time, those spins will relax back, and your brain actually becomes a source for the same radio frequency that went into the head, for example. So what we really need is we only have a certain amount of power that we can generate from the spins in the brain. And so we really need to maximize the signal coming out, which means we need to be very efficient in coupling the energy coming out of the brain into our coil, for example. So how do we do this? So here, I propose that we use these dielectric pads for high signal to noise ratio magnetic resonance imaging. And just this little cartoon, I don't show the coil here, but what we're essentially doing is we're putting a dielectric pad on top of the head. And here we can make this pad a slurry of water and high permittivity powder, or we can actually make it a monolithic pad of a ceramic material that basically has a certain permittivity. The permittivity values I'm talking about are somewhere between 150 and 10,000. Just for reference, the permittivity of water in the head with all the other parts of the brain is somewhere between 50 and 70, depending on the frequency. So we have something that's between 50 and 70 for the permittivity, and we're trying to couple in this higher permittivity. And I'll talk about the physics of this in a minute. But essentially what we can do is we can look at the geometry of this dielectric pad, say, for example, the thickness, and we can look at the permittivity and optimize it to get the signal in and out of the head. Some of the first experiments that were done at the University of Leiden in collaboration with Penn State shows this effect. So here in this case, we have this pad shown here, and we don't see the coil. And on the other side, we actually have a water pad that's not really shown. It's actually deuterium. And what we're doing is comparing the signal strength in these two different regions. And what we can see is the signal strength with this pad increases about like a factor of 2, somewhere between 70 and 140%. And this work was done by Andrew Webb about a decade ago. We supplied the materials, and it really generated a lot of interest in this coupling of the signal in and out to really increase the signal to noise ratio. So a lot of work since then. One example of some designs we're doing, this would be an example of someone within the tube, and you can see here this little cutaway. We have the coil shown here, and what we're doing is we're designing these dielectric pads. This would be shown here in a blue here, where we basically can then couple electromagnetically more efficiently from the coil into the head and back again. So we could do it we could actually make the pad actually as a structural unit of the helmet as well. So this is some of the current research. Recent publication shows this. So this is a helmet that we made. This shows the dielectric helmet that we have. This unit here is the coil structure shown here. And then we have basically a receive array, and we have a transmit array. So actually the coils are separated, but what we want to look at is the effect of with and without this helmet here on the signal strength. So there's a lot of plots here of a test patient. And here we're looking at without the helmet and with the helmet. And here we're looking at the transmit efficiency in terms of microtesla per watt produced. And we can see here that we can see an enhancement when we add the helmet to the array. But more importantly, we can see that we see an enhancement in the signal to noise ratio when we add as well. So this shows some promising results, just very recent, on using these dielectric pads to couple the signal in and out. And then, of course, then the really interesting part is, what's happening physically. And, there's lots of concepts electromagnetically, but you look at displacement current, impedance matching, and resonance. I won't get into these in detail, but I wanted to show a little bit about how we're thinking about this problem and how we're thinking about electromagnetically increasing the signal into the brain. So let's talk about the first one. It's called displacement current. And from your fundamental electromagnetics, you know that the displacement current essentially is something that is related to a time varying phenomena. So here we have a capacitor, and we have this current going in and out. The current, of course, is moving charge on these plates. That moving charge essentially creates this magnetic field, which then creates this electric field. And essentially that's the displacement current, because we don't have a conductor between these two plates. And so that's sort of the fundamentals that you had learned probably in electromagnetics. And so that's the first sort of concept that we need to think about when we think about this signal going through the dielectric, because the dielectric is an insulator, like the material that would be placed between these two dielectric plates. So let's just do a little experiment here with some Helmholtz coils, and we can then look at the current going through these Helmholtz coils. It's an AC current, and we can look at the contributions to the magnetic field. And there's actually two contributions. One is the coil current. Coil current generates a magnetic field, but then we can also look at the displacement current, the time varying response of the electric field. And that displacement current has this permittivity concept in. So this is where the dielectric concept comes in. In this case, the dielectric is just a circle. It's a disk that's located between these two Helmholtz coils. So what we can then do is look at the relative contributions of the coil current and the displacement current for various disks that have certain permittivity values and dimensions. So here we can look at, say, for example, resonators of disks. We're actually below the resonant frequency. So it's not really, in this case, a resonant response. We're actually just looking at the displacement current below resonance. And here I'll show for a free space wavelength at 3 Tesla, which is 125 megahertz, I'll show what the magnetic field looks like. That's in this slide here. So there are some simulations showing the effect of the ceramic disc, the high permittivity disc shown here. And as we can see, here's the baseline data without the ceramic discs. And as we start adding the ceramic disc, we can see an intensification of the magnetic field from that displacement current. So it's just some fundamental ideas around why we use dielectric materials to enhance magnetic fields. The other thing that was interesting is if we actually just put a dielectric block within this MRI coil setup, and we put that block within water because we need protons actually to see the signal. Here we can compare two different magnetic field MRI units with two different permittivity blocks. So here we can see that we have the experimental and the simulated data. We have the block shown here. So that would be this scenario here. And then if we take the block out, that would be this signal strength here. So we're actually just looking at one of the faces of this cube, one of the slices, and we're comparing then the strength of the signal, that's what this B1 plus is, with and without the dielectric block. So you can see here the intensity gets quite large when we add a dielectric block to the water cube. And then we could also see here the simulations basically show the same thing as our experiment. So again, just another confirmation that this dielectric displacement current is what we're really looking at when we're increasing the signal strength. And of course, if we go from that dielectric block to something like a helmet that I showed, we're really looking at these displacement currents in this way. We've done a lot of simulations to really optimize the helmet dimensions and the permittivity values then to couple with these different coil configurations within MRIs. And there's several publications. Another one is shown here. So that's one of the things. The other way to think about it is impedance matching. So here we're trying to, again, maximize the RF transmission across interfaces. We're using this dielectric layer thickness and permittivity to control impedance matching between the coil and the brain. So that's just another way to think about it. If we look at the coil here, just a cutaway, and we're trying to get as much of the signal into the brain or head as possible, what we want to do is think about this pad in terms of the dimensions and the permittivity value so that we minimize the reflected RF wave and we maximize the transmitted. So it's basically an impedance matching layer, right? Just something like even someone in optics would do for, say, matching, say, a coating into a window or something like that. And here we're looking at the effect of wavelength. So this becomes very important in looking at the wavelength of the electromagnetic wave within the dielectric and how that's affected by the permittivity. You can see basically related to the square root of the permittivity. So the higher the permittivity, the smaller the wavelength within the dielectric material. So just a little comment on that. I won't get into it today, but we've explored this concept with all these different MRI units going from 1.5 Tesla to 10.5 Tesla MRI units. And what that means is that our proton frequency, our RF frequency, goes from 67 all the way up to 440. And we've actually tried these different pads on each of these systems. And we found generally that we need to be in this wavelength range, about 1/8 of a wavelength in the dielectric pad that gives us the optimum result. So it's just another way to look at coupling this RF wave into the body from a coil. And then finally, the other concept that we want to look at is resonance. And this is a little bit different. The last example I showed you really was just looking at a one-dimensional problem. We're just looking at the thickness of the dielectric layer and how that relates to the fraction of the wavelength. But also we can do resonance structures. So basically we're bounding the electromagnetic wave in all three dimensions. So here, I like to think of resonators in this way as a musician myself. I think of resonance related to size. So obviously lower frequency tuba, higher frequency trumpet. But the same thing occurs in these dielectric resonators. We have to have a certain size associated with them. And then we actually control the dimensions and the permittivity value. So lots of results here as well. Just some examples from literature where we have a dielectric resonator antenna on an ankle shown here, giving a very nice image. This one is one that was done, I believe, in St. Petersburg, where very recently they did some breast imaging using dielectric blocks and then found an enhancement in the signal to noise ratio. And then here, just kind of reiterating what we did on the zebrafish. So these are all dielectric resonators, a little bit different concept than the previous ones I showed you in terms of impedance matching, because here, not only do we control the thickness, but we also control all the other dimensions. So let me just summarize here. A lot of work done on optimizing the permittivity for all these different scenarios. So the operating frequency of the MRI depends on the field. So you'll see here that, for example, you have a proton at 7T operating at this frequency here. Actually, sorry, this is deuterium. Here's a proton at 3T operating at 125. Here's a proton at 7T operating at 300. So for the same nuclei, basically we can see this increase in frequency of operation. The other thing we're looking at are a variety of different X nuclei. So we're looking at oxygen, we're looking at sodium, and we're looking at phosphor. These are all really interesting if you're looking at, say, for example, ATP and looking at the spectroscopy of what's going on in the body as it's metabolizing, for example. So here we're optimizing for all these different scenarios in terms of the permittivity of the pad. So just another way to think about sort of designing these materials around what's needed in the MRI community as we start looking at different X nuclei. As you can also see, though, the permittivity values are getting quite high and the frequencies are getting quite low, and this is getting to be quite a challenge in this range here. All right, let's move on. So hopefully you have a better sense of why we're interested in dielectric materials for magnetic resonance imaging. The next thing I'd like to talk about is dielectric materials for 5G. And the trends are pretty clear. So in the past, say for 4G, we see antenna systems that look like this, at least in the US. I can look out my window and see these things on campus and close to campus in terms of these towers. And the frequency range in general is between 700 megahertz and 2.7 gigahertz. And what's happening right now is that we're expanding these stations here to go to lower frequency and to higher frequency. I would say most of the activity people talk about with 5G is something called sub-6. So in that sub-6 between say 3 and 6 gigahertz, there was a huge amount of spectrum actually auctioned off in the US, and companies like AT&T, Verizon, and T-Mobile really sort of had a bidding war over this part of the spectrum. And then what's also happening that's interesting is these high frequency bands here into the millimeter wave. So really pushing up into the 40 gigahertz range. And so now things get really interesting. It's really a game changer in terms of the technology as well, where we actually have different antenna systems and also think about bringing these much closer together. So instead of having these things kilometers away, now we have to think about maybe things that are meters away in terms of these antenna systems, and that's going to create a lot of infrastructure. On the material side, we tend to think of materials in this very fundamental way when we think about dielectrics. So what I'm plotting here is the dielectric constant or permittivity. We've talked about this permittivity value before. It's the ability of the material to polarize. And then corresponding to that is the loss. So as we start looking in the 5G frequency range, which is right here, what we're really looking for in our materials is contributions of a dipolar response, especially in polymers, and also a contribution in ionic response. And then I'll give you an example of an ionic material, glass. And we're trying to figure out how these tails of these loss peaks come into this range and really affect the electromagnetic propagation within this frequency range. And we have lots of ways to measure this. So this is just sort of a schematic on how we think about measuring materials within this frequency range. And remember, I'm focusing somewhere into the megahertz to 100 gigahertz range. So we're really in the space of where we use vector network analyzers. And we're also in a space where now the electronic sort of measurements that we typically do are really becoming more free space and photonic measurements. So it's really an interesting time to be exploring these sorts of megahertz, gigahertz methods for characterization and have a fundamental understanding of the materials. And over the past 3 to 4 years, we've really expanded our capabilities. So looking at all these different techniques, and here we're looking at the frequency range in which these measurements occur between, in this case, it'd be 10 to the minus 2 hertz. So we're at 10 millihertz, so very low. And as we go up 13 orders of magnitude in frequency, we can see that we move from something that's a very straightforward parallel plate method all the way into all these different techniques shown here. And it takes a lot of work to measure these properties above a gigahertz. So whereas maybe 1 or 2 techniques was sufficient to measure properties down here, now we have many, many more techniques to develop to measure dielectric properties in this frequency range between a gigahertz and up to a terahertz. So this is our focus for 5G. All right, let's provide an example. And one of the best examples for us, because we have so many different techniques, we need a lot of different kinds of samples. And because of these large number of samples, we found that measuring 3D printable dielectrics, basically polymers, is a good way to get started, just to compare all our different techniques and really get an understanding of how things fit together across the frequency ranges of interest. So we have ways of doing a lot of different shapes, not to say that this is the shape we use for our characterization, but it gives you an idea that we can make things that are from centimeters, millimeters, all the way up to tens of centimeters in shape. And that's really important as we start exploring these different techniques. So just to give you an idea, this was an acrylate polymer that was 3D printed. And we have all these different techniques. We're measuring the dielectric permittivity from very low frequencies, shown here 100 hertz, all the way up into the 100 gigahertz range. And what we can see here, the permittivity value at low frequency drops from about 4 for this acrylate polymer down to something around 3. And as you can see here, some techniques work better than others, but we have a lot of agreement in these techniques here. above 10 gigahertz. And we have cavity methods shown here. We have free space methods shown here. Either free space in this way, or actually this is considered a transmission line space one. So we have a lot of different methods, and it's really important to develop all these, even though we only get, say, 1 or 2 frequency points here. It gives us a real good idea across this whole spectrum, which is related to 5G. So this is the permittivity as a function of frequency. What we can also do is measure the loss. Remember that we need to measure both the loss and the permittivity to get a fundamental idea of what's going on with our materials. And again, as we go from 100 hertz all the way up to 100 gigahertz, we can see sort of general things occurring. We see this dielectric relaxation peak shown here. I don't have it completely filled in because, again, we have some spaces here where we can't do the measurements easily. But in general, this peak here is very interesting. And then the question is how things kind of push up in loss as we go to higher frequency. Loss is a critical component of any design. And we need to really understand the materials as we put them into devices. And one thing we've learned here from these types of measurements is these neat little sort of interpretations of a dipolar response aren't so trivial. And because of the complex nature of these polymers, we really have to think about, the basically long chains and short segments and how they basically smear out this response. And these tails really start pushing up into the 5G range. So as we explore polymers, it's going to be really important to understand the structure of those polymers and how some of these orientation or dipolar responses push up and really push loss up in this frequency range of interest. And so, there are specific materials that we're looking at for 5G applications. Next, I would like to talk about the ionic contributions to the dielectric response, either the permittivity, the real part, or dielectric constant, or the loss, and how these tails will come into the 5G range. Let me just talk about glass. It's a really important material in microwave and millimeter devices. It's used a lot in something called low temperature co-fired ceramics. These are used in very sophisticated packages as we get to miniaturization for 5G. All cell phones have low temperature co-fired ceramics as part of their package. And those packages have a glass component as well. I know companies are also looking at glass as a potential substrate. And so then we're looking at how we apply these glass substrates above 30 gigahertz. And of course, if you do microwave cooking, you might use one of these glass sort of things or put glass containers in your microwave source. So that's another thing you'd probably be thinking about as you couple the electromagnetic waves to your food and hopefully not to your glass. All right, so if we do a comparison of crystalline and amorphous, remember these are silicon oxide, both are the same chemically, they're both SiO2. And as we compare the response at say 9 gigahertz, we can see the permittivity values are here, but we have an order of magnitude difference in this loss, and loss becomes very important for a lot of these applications. And what is causing, basically for the same chemistry, this higher loss? So that was our big question, and it really is related to structure. And once we start thinking about structural aspects and how it relates to permittivity, there's a lot of literature out there from, say, the 1990s and 1980s that relate permittivity to structure through something called Clausius-Mazzati. And so this is a pretty traditional approach that works really well for permittivity and actually index of refraction, where in this case, though, we're looking at permittivity is related to density. It's basically how many atoms can you pack in a volume, and each atom is a polarizable unit. And so the more of those polarizable units you have within that volume, the higher the permittivity value will be. And then each one of those polarizable units you need to characterize as well. So each atom or ion will have a certain polarizability. So it's the amount of polarizability within each individual ion and how many of those ions or atoms are located within a volume. So those are the two contributions to permittivity. It's been done for crystal materials, and it's done in a very, very systematic way. So this publication has thousands of citations. Shannon basically took a bunch of minerals, mainly silicates and I think fluorides, and then looked at the permittivity values And then from there, he was able to assign a polarizability for each of these ions. And so in this case, for quartz, we can then take the polarizability, SiO2. So you take 2 of these oxygens, so that's going to be 4. And then here you're going to add silicon, so it's going to be somewhere around 4.8 something, right? So that's the polarizability of silicon oxide. So what we can do then is we can take that polarizability value from the table. We can measure the density and we can figure out how many atoms per volume we have. And from there, through this Clausius-Mazzati relation, we can get the permittivity prediction. So it's a pretty straightforward equation that relates then the polarizability and the number of ions per volume. And that's a pretty straightforward calculation. We can see here from that polarizability from that table I just showed you that we would calculate a permittivity value of 4.55. And indeed, if we look at literature, this is the case. If we take that same polarizability value for fused quartz or the amorphous material, we underpredict the permittivity. As we see, the measured value is 3.8, but here the predicted value is 3.5. So what does that mean? Basically, we have an extra polarizability or an extra polarization in glass. So we would need this polarizability value in our CM calculation to match the predicted and measured values. Okay, well, that has a profound effect on dielectric loss in the 5G frequency range. So we have this extra polarization mechanism. Here we're looking at the permittivity and loss as a function of frequency, and it's pretty flat in terms of the permittivity, and we start to see a roll-off as we get into the terahertz range. Correspondingly, we're starting to see, even at lower frequencies in the 5G range, this tail coming up for the glass, and then we think we see a peak here. This is where some more research will need to happen to make sure, we understand where this peak occurs for the fused silica. But what's really interesting, quartz doesn't have this. So that quartz sample, we can see has a very low dielectric loss and no peak here. So there is a fundamental difference, even though the chemistry is exactly the same, between the crystalline and amorphous structures. So if we look at this, we think basically what's happening is this tetrahedral rotation. It's actually maybe more of a dipolar response in glass, but we also have some of these influence of these coupled modes and anharmonic modes in the IR range that really pushes down here as well. And again, I won't get into details here, but certainly we'll welcome questions specifically about this. But as we look at loss values in the 5G range, I think both these will be important also for glass, both these mechanisms. And why are we so interested in glass as well? As we start pushing up to higher frequencies, glass is a huge structural material. And as we start pushing into the 40 gigahertz range, a lot of internal office spaces and even outside will have these 5G antennas that will basically be finding receivers, either at a desk or a mobile phone, and they'll be rastering around and bouncing off all these different surfaces. So it is important to understand the dielectric properties of glass and maybe how to modify them to either enhance transmission or reflection of these different signals. So just window glass, if we move from pure silica to something that's window glass, it's still mainly silica, silicon oxide, but it has a lot of additives, modifiers like sodium oxide, calcium, and magnesium oxide. And so a typical window glass composition has this, as I said, mainly silica, but some other modifiers shown here. We actually just looked at window glass samples and were able to measure the dielectric properties over a broad frequency range. So in this case, I'm only going to show the loss, but here's the quartz shown here. Here is the pure silica. So again, the same composition between the quartz and fused silica. But as we start adding these modifiers, we see their contributions even at lower frequency in terms of the loss. And then as we get to higher frequencies, we're just starting to see this contribution of the silicon oxide here. And I would love to get to higher frequencies to see where this will roll off, and we can understand perhaps the contributions a little bit better of these silicon oxide and tetrahedral rotations. Okay, so again, just to summarize this, is we're very interested in this frequency range for a lot of applications. Fundamental material properties need to be understood, and we're looking at the effects of structure and chemistry on the orientational dipolar response and the ionic response of materials, mainly in this frequency range of interest. And just kind of going back to that Clausius-Mazzati, we have a recent publication shown here where we look at quartz, a very ordered structure, polarizability shown here. As we talked about in a previous slide, the polarizability calculated we would need for amorphous silica. It's a disordered structure, a little bit extra motion in that, and we get a higher polarizability. As we start adding silicates and modifying and opening up the structure, just looking at the polarizability of this silicon oxygen tetrahedron, we can see again a slight increase. And this is all this detailed in this publication here. And then as we add even more modifier, in this case would be a calcium, the polarizability even goes up further. And then we see that we're breaking up the structure even further. So there is some really good correlations between the fundamental ionic performance of a structure and the polarizability and eventually the loss. So let me just conclude. Hopefully you have a flavor of how exciting it is to look at electromagnetic properties within this frequency range. And I think in the future, this is going to be more of a style of research where we do a lot of materials research. We understand properties. I talked a lot about material properties today, how those properties are related to structure, but also how to make these materials into something like a helmet here. So all these on the material research side are important, but what's really driving it and what's really exciting is all this electromagnetic simulation. It's become ubiquitous and accessible, right? So all these different methods, there's lots of different software packages out there. In my undergrad sort of courses, I teach some of this as well. You don't have to be an expert to use them. You might have to be an expert to understand them and realize what the electromagnetics are doing. But I think it's really driving a lot of research, especially there's no way you could design a helmet like this without this sort of a simulation. And the investment to make something like this is just incredible. So you better have a pretty good design before you make the materials into a shape like this. And then finally, as we start looking at designing different structures, we'll need the simulations to do that, but then we'll need all the property inputs into that simulation. So it's going to be this interplay between structural design, simulation, and materials that will really, I think, drive a lot of these technologies in the future. You need to have them all coupled. So I think with that, close and thank you for the opportunity, and really looking forward to some new ideas through discussion and collaboration. Thank you very much.
Right. Thank you very much, Mike, for that great talk. Really appreciate it. So
Pleasure.
is now open for questions. Who'd like to start? So yeah, Franz, go ahead.
Yeah, very interesting talk. I have one question related to polymers. You mentioned that in some applications also polymers are used as dielectric materials. Are they compatible with industrial processing conditions? And how about aging?
So in terms of the polymers people are using at the moment, they call them liquid crystal polymers. They're highly crystalline. And for the same reason I showed the difference between quartz and fused silica, I think is the same reason why people use crystalline polymers, so LCP. So they're currently being used on the market. There's companies like Rogers who makes these. It's interesting to think about sort of oxidation of a polymer and degradation of a polymer in some sort of environment like a radome, right? So you have all these antennas and you have a polymer radome on top. How will that affect the millimeter wave performance? I think is going to be interesting because you're going to oxidize, you got to break up these molecules, and you're probably going to get more loss, I would guess.
And how about fabrication? How are those polymer structures incorporated into the devices?
So lately it's mainly packaging. So these are like printed circuit boards. And so
okay, I see.
Yeah, that's probably where most of them are used.
Thank you.
So Mike, I have a question on the dielectrics. So as we keep pushing up these frequencies, right? So people keep saying 5G, and then now it's about 6G, and as we keep pushing up the frequency, are there fundamental limits on dielectric material that can be designed, or we
Yes.
have availability of materials in all these high frequency range?
So as we push up in frequency, you know, we love ferroelectrics and high permittivity, right? Unfortunately, the permittivities are going to be lower and lower. So as we push up to say 1 to 200 gigahertz, actually air is your best dielectric. So it's going to be interesting. And obviously, how do you achieve that? 3M has products where they have spherical glass sort of things that you can put into polymers. And so lowering the permittivity that way. So I think the trends will be that less is more. You're going to have less and less polarizability, because then you don't have a contribution to loss.
It's a very, very tricky problem, actually. And the other thing is the impedance matching. So a lot of time, so for example, in wireless power transfer, we want to send signals in the air far away. But yeah, we have to find a way to send signal in air, and that's another big challenge, that we need some kind of matching dielectric layer to provide impedance which is similar to that of the medium. Again, low permittivity materials.
So that if you look at the guys, NIST, Nate Orloff, he talks about this quite a bit. So because of transmission losses, that is the biggest drain on your battery for your cell phone. And so as we go to higher and higher frequencies, it's going to be a bigger issue. And, you know, people talk about making better batteries, but the other side of it is you need more efficient transmission to help your battery life.
Yeah. Other questions from students? Any? So I know sometimes the magnetic world has a little bit, so this is where ferromagnetic versus ferroelectric comes in. The ferromagnetic world is a little bit more advanced in terms of designing magnetic materials with very high FMR frequencies. But equivalent doesn't exist in ferroelectric world, that we don't have very good ferroelectrics with very high dielectric resonance frequencies. And so but you would like both of them to be at the same time in order to do, for example, impedance matching in antennas, that you would love to have very high permittivity and very high permeability at the same time.
Right. So the gyromagnetic response can go to high frequency. It's really interesting. So within the cell phone market, there is these bulk acoustic wave and surface acoustic wave devices, right? And so they're used a lot for filters right now. And what's happening, the industry is getting to the point where as you go from 4 gigahertz even to 6 gigahertz, the dimensions of these devices are becoming so small that the manufacturing tolerances are becoming untenable. And so now what will happen is the dielectric resonators will come back again. So in the 1990s, dielectric resonators were everything. Motorola sold billions of these. And then these little bulk acoustic wave devices took them away. So $1 billion market just gone. And so now what's happening is the dielectric resonators are coming back because the frequencies are high enough that the bulk acoustic waves can't do it anymore. So to me, it's really fun to watch that sort of transition from a dielectric resonator to an acoustic one back to a dielectric again. Yeah, you just have to be around long enough to see these things.
So I know friends at Kiel, there's also a lot of work in magnetoelectrics for MRI imaging. And maybe the Eckert and other folks will probably can have a good conversation with Mike.
Yes. Yeah.
About
yeah. Eckert would have attended the talk, I'm sure, but as I said, he's on vacation.
Yeah. So there's a lot of work there, Mike, going on alternative, basically solid state imaging systems, which are alternative to MRI. By using magnetoelectric transducers, and I think they would love various ways to suppress the losses. And So this could be a nice conversation between the imaging
I
systems.
can mention to Eckhart that the talk was recorded and that he and his people in his group should
Yeah.
listen to the video recording.
Yeah, I think they would love probably to engage with Mike and benefit from his experiences.
Yes.
Great. It seems like, Mike, there's no other questions. So thank you again so much for this great presentation.
Pleasure.
And
Yeah, it was great.
yeah,
Thank
and
you,
I
Mike.
said, yeah, and as I said, there is a lot of interaction between Kiel and Penn State. So one of the things we want to do is bring also students from Kiel to Penn State for a short-term visit. And so this could be an opportunity for a student or postdoc from Kiel to come and work with you and basically learn about the dielectrics and electrics for high frequency applications. This could be a nice project for somebody at Kiel.
Yeah, that'd be great.
Yeah. So thank you so much. Thanks everyone for attending. This was a great seminar. Have a good day, everyone, and enjoy. And thank you very much, Mike. Yeah, thank you.
Bye.
Bye-bye.
Bye.